Everyone, welcome back to
SSD seminar this week.
so today we're honored to have
Professor Yue M from Harvard to give us a talk. Yue M is received his PhD from UIC, and he's now a Golden McKay professor in E at Harvard. So his research interest is mostly in mathematical foundation of statistical signal processing and machine learning. And his work has been recognized by many best paper awards in signal processing conferences. And recently he has been recognized as signal processing, IEEE Signal Processing Society lectureship, leadership. Right? And so with that, let's welcome Professor Yue M for his talk on understanding universality in high dimensional estimation and learning. So let's welcome.
All right. Okay.
Thank
you very much. Thank you for the introduction. Today I'm going to present our recent work on understanding the so-called universality phenomena in the context of high-dimensional estimation learning. So what is universality? On a high level, let me see if I can move my slide. On a high level, universality refers to the general observations that many large and complex systems are asymptotically equivalent, although they can be very different in their detailed constructions. And I'm going to give a few concrete examples to exactly explain what I mean by large systems being asymptotically equivalent. The first example should be familiar to, I think there's a range issue, so should be familiar to all of you. So suppose we are given a collection of independent, identically distributed random variables. The requirements are that they have zero mean and the variances are equal to 1. Now, if you take the summation normalized by root n, then the central limit theorem tells us that as n go to infinity, this left-hand side converges in probability distribution to the standard normal random variable, right? Now, this is a very simple example of universality because the actual probability distribution of these random variables are irrelevant. For example, these random variables can be discrete random variables equally likely to be plus or minus 1, or they can be shifted versions of exponential distributions. You still have the central limit theorem. And in probability theory, there are other universal laws. For example, instead of looking at the summation of these random variables, we look at the maximum of these independent random variables, then we will get the extreme value distribution, which is another class of universal distributions. The second example I'm going to give is about random matrices. So suppose we want to construct an n by n matrix with independent random entries. So aij's are all independent random variables. Again, the requirements are that they are mean zero and univariance random variables. Now, it's very easy to do this simulation on your computer. You generate a large, for example, n equal to 2000 random matrix, and you compute their eigenvalues. Because this matrix is not symmetric, the eigenvalues are complex values. So you're going to plot the n eigenvalues on a complex plane, and this is what you will get. You can see that although the matrix itself is random, all the entries are random, the eigenvalue, the distribution of eigenvalues are close to a uniform distribution over the circle. This is known as Genevieve's circular law. Again, this is an example of universality because these random variables can have pretty much arbitrary probability distributions. They can be Gaussian, they can be uniform distributed on plus minus 1, and so on, right? Now, similar to the case of central limit theorem, the universality phenomena for this independent case is fairly well understood. In this paper by Tao and Gu, they have shown that indeed, if you have a matrix with independent entries, and as long as you make sure that the first two moments satisfy these conditions, then the density in eigenvalues are close to a uniform distribution of the circle. But I want to emphasize that the universality phenomenon itself is much more general or more robust than what existing theory can show. For example, a very important question is randomness in the matrix entries critical are they essential to have randomness? What if I have a matrix that is deterministic, right? Now, one example is the following. Suppose we fill A with entries of pi. Okay, what I mean is that if you have a 3 by 3 matrix, and then you're going to fill the first row with 3, 1, 4, second row 1, 4, 5, 9, and so on and so forth. Okay, but you want to do it for large n, and you can still plot eigenvalues on your computer, and this is what you would get. You have the same picture. All right. As far as I know, this universality phenomenon for this fully deterministic system is still open because it has to do with some conjecture if the number pi or square root of 2 is sort of a regular number. In this talk, I'm going to consider universality phenomena for some so-called nearly deterministic systems. They're very far from these fully independent systems on the left. They're very much close to the fully determined systems on the right, but we just need to add a little bit of randomness to have the proof go through. Yeah. Now, the last example I'm going to show comes from signal processing. This is a phase retrieval problem, but the setting, mathematical setting, is very simple. Suppose you want to estimate a vector Psi. Psi can represent an image you want to reconstruct, and you observe it through a physical system that can be modeled by matrix A. So in principle, what you observe is A times Psi, and A is known from your given physical system. This will be a very simple linear inversion problem. But in phase retrieval, you just add a very simple twist. Instead of observing A times Psi, what you observe are the absolute value squared of A times Psi. So in this case, if you have a entry -3, what you observe is 9. You are missing the plus minus 1 sign information. Or in a complex value case, you would have lost the phase information. That is why the problem is called phase retrieval. And this problem arose in classical imaging applications, but there are also other problems with similar mathematical structures, such as blind deconvolution, channel estimation, and so on. Now, if you want to study this problem, there are a few questions that you want to ask. First of all, what is the fundamental limits of a phase retrieval problem? How many samples? Perfect reconstruction, right? Or to guarantee weak recovery. By weak recovery, I mean
Hi, sorry to interrupt. We on the internet cannot hear you anymore.
It's muted on the screen.
No, I think this US.
this is my laptop. My laptop is muted. Okay.
Can you use?
Great.
Okay.
All right. Okay. Great.
Sorry.
Sure. Okay. So this is a setup, and then this imaging setup can still be represented by an underlying sensing matrix, but this sensing matrix has a particular block structure where each block is a product of F, the DFT matrix representing the Fourier transform, and lambda I, which is a diagonal matrix, with diagonal entries are drawn from +-1, +-I. This is just a mask. Now, if you have this is one block representing one experiment. The next experiment, you can change the phase modulation mask, you use a different diagonal matrix, and so on. Okay? So this is clearly much more challenging to work with theoretically than the previous ID type of assumption. Now, there's been some work analyzing performance of phase retrieval or related problems with this kind of structured random matrices. For example, one of the best guarantees in the literature is that to reconstruct the underlying vector, the number of measurements m, the number of rows here, must be greater than the constant times n, the dimension here, times log n to the power 4. So there is an additional polynomial log factor. If you do a very simple back of envelope calculation, n is a dimension. For example, if you want to reconstruct a megapixel image, so n equal to 10 to the power 6, log n to the power 4 is greater than 36,000. So this is clearly a very pessimistic type of result, or this is a very loose type of bound. Fortunately, we can exploit universality. We can do some experiments. So here, let's consider 3 different sensing matrices. The first one is the type of matrix that we want to study. This is a block matrix where each block is a Fourier transform times a random diagonal matrix. The second type of matrix that we consider is a so-called randomized DCT. So DCT stands for discrete cosine transform. You can think about it as a real value version of Fourier transform. You start with an m by m discrete cosine transform matrix, and then you randomly select n columns. The reason that we need to randomly select n columns is just to make sure that this matrix has the same dimension as the previous matrix. Okay, but otherwise the constructions are very, very different. The third construction we call Haar. So let me explain, because we're going to use Haar distribution quite a lot in the rest of the talk. So let me explain what I mean by a Haar distribution. Imagine you have a set of all possible orthogonal matrices of a given size, and then you define a uniform distribution on a set. Okay, and then this is, in our case, we call it a Haar distribution on a set of orthogonal matrices. Or intuitively, you can think about a matrix drawn from Haar distribution. It's just a random rotation. Okay? It's a random rotation in n-dimensional space. Okay? All right. So what I mean by the Haar distribution is you draw this random orthogonal matrix, and then you pick the first n columns. Again, I picked the first n column just to make sure that I end up with an n by n matrix. So you can see these 3 matrices are very, very different in construction, but we can do experiments. In this case, we run a particular algorithm for phase retrieval with a so-called spectral method. The detail is not so relevant here, but what we show here is the performance of this algorithm on the 3 different sensing type of matrices. And here, the horizontal axis is the sampling ratio, the number of samples over the dimension. Okay? If you move toward the right, you have more samples per dimension. And the vertical axis is the correlation of your estimate and the true signal. The higher, the better. You can see that the 3 different sensing ensembles, they are essentially following the same underlying curve, right? Okay. So, and this underlying curve is a theoretical curve derived for the Haar type of sensing matrix. So for the Haar sensing matrix, it's possible to derive the theoretical curve, which is a blue curve. But then this blue curve can also accurately predict the performance of this block matrix or random DCT matrix. Okay. So this is another example of universality. And I want to mention universality is a quite ubiquitous phenomenon. This is also just another test. So so far we have only been talking about spectral method. So we might wonder if universality is only about the eigenvalue or eigenvectors of random matrices. But I want to claim that universality is beyond only eigenvalues and eigenvectors. For example, we can look at different algorithms for phase retrieval. This algorithm is so-called phase max. Again, the detail doesn't matter. It's a reconstruction algorithm based on linear programming. And what we show here is the mean squared error of this linear programming based method on these three different sensing matrices as a function of the sampling ratio. You can see, again, they fall right on top of each other. And the last one is a vertical flow. Again, this is just, you can think about it as a gradient descent, but they're actually solving the underlying optimization problem. You can see for every iteration of gradient descent, the performance of this algorithm are the same for the three different sensing. Right. Now, I want to mention that universality is pretty ubiquitous phenomena. It has been observed in different fields, for example, in statistical physics, in communication systems, and also, of course, in compressed sensing. Now, it has also been observed in machine learning. For example, in this paper, they've shown that the sound output from a GAN model is asymptotically equivalent to a Gaussian mixture model, which allows you to do further precise analysis. It's also being observed and exploited in other fields like randomized sketching, hashing, and so on. Yeah. So I want to use this slide to argue why we want to study universality. Of course, this is intellectually a very interesting question to understand why this is happening. But what I want to emphasize is that there are also practical consequences of understanding universality. So imagine you want to understand a given system A. For example, this system will be the performance of phase retrieval on this coded diffraction pattern matrix, the block structured block matrix as a sensing matrix. But this matrix is too difficult to analyze. It is beyond the reach of our current mathematical tools. But if you can show that this system is in the same universality class of two other systems, B and C, for example, B and C can be the Haar matrix or random DCT, then you can study instead system B because it has additional structures that we can work with the understanding that the properties that you derive from B can be carried over to A due to universality, right? So in some sense, universality is a true blessing of dimensionality. When you're working with high-dimensional systems, you get to play this kind of game by studying a much simpler system, and you get the same result that can characterize the original complicated system. Yes, question?
Yeah, so it seems like this would only work if transforming like from ACDP to AHAR was not like just as complicated as solving ACDP in the first place. So like, how do you guarantee that it's easier to transform to another problem and then solve it?
So this is something to be proved. So so you need to prove indeed. So numerically, first we believe they are equivalent, but we still mathematically need to prove it. Yeah. So I'm going to show you some of the works that in understanding the mathematical reasons that they match.
How do you show that transforming from one to the other is easy? Like,
so here what you are saying is these are just two different matrices. You use the same algorithm to actually do the estimation.
Okay.
But the point is, if you want to analyze the performance of this algorithm, for example, what is the asymptotic mean squared error and so on, then this type of matrix is much more difficult to analyze. Ideally, you want to work with either Gaussian or these kind of highly random systems. But if you have universality, then you get to assume your sensing matrix is these kind of highly random systems.
okay, thank you.
Yes, Qin?
Yeah, I just want to ask the same question.
Okay.
How can you prove the
Yes, so this is what I'm going to show some recent progress in rigorous understanding this type of universality. Yes.
Hi, Paulson. And before we move to the next section, I have a question about why in the beginning, why the A matrix is constrained in a circle-shaped distribution. Why it is a circle?
Oh, circular. Yeah. So
why is it not rectangular?
Yeah, it's going to be. If you haven't seen this before, then it's supposed to be a very surprising, highly surprising fact. Yeah, it is the same reason why. If you have a symmetric random matrix, then the eigenvalue, which are real in this case, will have a semicircle distribution. But exactly why? then there are different reasons. You can say if you plot them, if you compute the moments, and the moments are Catalan numbers, they are exactly matched the semicircle. If you do the Stieltjes transform, then they satisfy a fixed point equation. You solve it, you will have this. Yes, but it's supposed to be highly surprising. There's no reason to know right away this is going to be the case. Thank you. All right, great. So in this talk, I'm going to present some of the recent work on understanding universality phenomena in two different parts. The first one is about universality in these high-dimensional estimation problems, and the second one is about some universality questions in the context of machine learning, for example, kernel methods and random feature models. So I'm going to start with the first part, and this is a joint work with my colleague Subhabrata Sen and our joint postdoc Rishabh Dudeja. Now the setting is classical for this first part. We want to estimate a vector beta star that's a target vector. Okay? And X is the sensing matrix, and epsilon is so the noise, and Y is our observation. So we essentially observe a noisy linear version of the target vector, and we're going to estimate beta star by solving an optimization problem where the cost function is a mixture of L2 loss and a regularizer. Okay, so if you have considered a special case of this regularizer, for example, L1, this is nothing but Lasso, but we consider general convex regularizers, so we can call it a generalized Lasso type of problem. So this is a classical setting and classical type of estimation problems. Now, once you have the problem, then the kind of questions that you want to answer theoretically are, for example, when the dimension is high, what is the mean squared error of your estimation compared to your true underlying vector? And in the high dimensional case, there are also interesting phase transition phenomena that you can observe and you can also study. For example, depending on different parameters of your system, either this type of regularized generalized Lasso problem will perfectly reconstruct the underlying vector, or there's no chance that you can perfectly reconstruct the vector. There are also questions of optimal design of regularizers and so on. So all of these kind of questions are pretty standard theoretical questions that you want to understand. Now, if you look at the literature, then people tend to make some idealization, some assumptions, and two very popular idealizations are: first, you assume your sensing matrix has independent Gaussian design. Okay? So this is a very convenient assumption. Or more generally, you assume the sensing matrix comes from so-called invariant ensemble. So this is a generalization. So what we have here is you write X in the form of a singular value decomposition, where sigma are the singular values and U and V are the singular vectors. And here you assume U and V are two independent Haar matrices. Okay, and Haar matrices, again, as a reminder, they are just random rotation matrices. And we like these kind of assumptions because there are a lot of very powerful and very convenient and very mature tools in the literature that allow us to study these kind of estimation problems or optimization problems if the underlying matrix satisfies these conditions. So here, it's just a list starting from non-rigorous method from physics to more recent development, such as minimax comparison inequalities, even out analysis, and so on and so forth. Okay, there's no shortage of tools, and it's a very nice playground for theorists. But in many practical applications, the type of matrix that you're dealing with are structured. For example, let me just give a few examples of structured matrices. The first one is so-called a spike and sign matrix. It has two blocks. The first block is a DCT matrix, discrete cosine transform matrix. The second block is identity. And it is called spike and sign because if you think about the columns of identity, these are spike signals, and the columns of DCT, they are essentially sinusoidal signals. So it's a mixture of two very different type of vectors. The second type of matrix example that I'm going to give is randomized DCT. So again, Q is a DCT matrix, and P is a random permutation, and lambda is a diagonal matrix. This type of matrix is commonly used in randomized sketching because this DCT matrix has very efficient implementation, right? So it's a full matrix but with structures. I want to emphasize that here Q of n does not need to be DCT matrix. They can be essentially any generic delocalized orthogonal matrices. I'm using DCT just as an example. Now, these matrices are very, very different from the statistical assumptions that people have been making. But fortunately, what people have observed is that there is a very strong universality phenomena that you can, and in particular, there is the following conjecture. In a high-dimensional case, the properties of these estimators only depend on a singular value of the matrix. The singular vectors are irrelevant as long as they are sufficiently generic. Okay, so this is the generic, the high-level intuition that people have. Just to make myself precise, suppose you have a sensing matrix X. You first do a singular value decomposition. So in the middle, you have a singular values, and then you construct a different matrix X tilde by keeping the singular values, but replace two singular vector matrices by two independent hard random rotation matrices. The conjecture is that in a high-dimensional case, if you run this regularized V-square estimator, then the performance on these two matrices are identical, okay, in a high-dimensional case, right? So we can do some experiments, and here we consider several different, very different constructions of sensing matrices divided into two groups. The first group will have one type of singular value spectrum. The second group have a different type of singular value spectrum. And in this first experiment, we show the mean squared error of running this estimation algorithm as we change the parameter of regularization. Okay, so strength of the L1 penalty term, for example. You can see that for matrices with the same singular value spectrum, they have identical performance. Numerically, you can observe that, right? And you can also run an algorithm. For example, you run proximal gradient descent for actually solving this problem. You can see for every iteration, matrices with the same spectrum have the same performance, right? They are very different in terms of their singular vectors. And lastly, I want to show you another way that we can demonstrate universality. If you look at the reconstructed vector, which is a high-dimensional vector, but for this high-dimensional vector, we can plot its histogram. You can see that for matrices with the same singular values, the resulting high-dimensional estimation will have this same histogram. Okay. Yes.
Do you assume beta is random as well, or just X is random?
So yes, so yeah, come to this point. Yes, so beta.
Imagine that if beta aligns with the eigenvectors, then the eigenvectors
Yes,
matter.
that's right. So currently we are assuming beta is independent. Yes, so there is a randomness in the beta. Beta is independent, drawn from some given distribution. Yes. Yeah.
Can you clarify for me too what the two lines are on each plot?
Yeah,
And then
so, yeah.
why
For example, if you look at this, the two lines, they are both a curve of MSE as I change the L1 regularization parameter. So the difference is that the first line, the line on the top, show the performance of three sensing matrices who have the same, essentially the same singular values. And the line at the bottom are the performance of another three sensing matrices with a different set of singular values. So you can see, so the point of these figures to show that the performance only depend on the singular values, but if you keep the singular value the same, singular vectors can be very different, but doesn't matter. So they have the same performance.
And then relatedly, why at the lowest lambda is the MSE not the lowest, right? Like by definition, I mean, am I right that it's MSE plus L1 penalty is the objective function?
So the objective function is L2 plus L1 plus L2. It's like elastic net. Yeah.
Okay.
And then we're changing the L1 parameter.
Okay.
Yeah.
And does the L2 elastic net part have a parameter that's just fixed?
Fixed. Yes,
Got
it's
it.
fixed. Yeah. Yeah. This is just a demo, like a slice of the parameter that we change. But again, this is empirical, just to convince ourselves that this is this is the case. Of course, this is a very well-known observation. It's also a conjecture that people have done more extensive simulations to demonstrate there is empirically this type of conjecture that the performance of this kind of high-dimensional estimation problems only depend on the singular values. And the challenge is the theory is very much lagging behind the observations. And there have been some progress in the literature before. For example, there's this line of work, so-called IID Gaussian universality. So what people have shown is that the matrix with IID entries behave like IID Gaussian matrices. So you can replace the Gaussian assumption by a sub-Gaussian distribution. So this is the first line of work in doing universality. But first, this is very far from what you want to do because you still require the matrix to be independent, have independent entries. And there is a further generalization, so-called correlated Gaussian universality. In this case, you assume matrices have independent rows, but within each row, the entries do not need to be independent. Okay, and in this case, the universality is that then this kind of matrix behave essentially like a Gaussian matrix with independent rows, but you just each row would have a different, will have a non-diagonal covariance matrix because they are not independent anymore. Okay? But again, they are very different from what we want to do. What we really want to do is a third type of universality for nearly deterministic matrices. And there's been some progress, mostly from the random matrix theory literature of looking at the spectrum of structured random matrices. In estimation, there's been some results in noises compressed sensing, a very particular setting that you can show that indeed for a large class of nearly deterministic matrices will have universality. And what we want to do is to make some further progress in understanding the last type of universality. Now, let's look at what the conjecture, what conjectures we have. The conjecture says that a performance only depends on a singular values. The singular vectors are irrelevant as long as they are sufficiently generic. But this is a very, very vague type of description. So it's actually what we mean by a singular vector being generic. Okay? This is the first thing that we want to address. So in our work, we defined a universality class that makes this kind of a genericness of the singular vector precise. Okay? So what we say is we're given a compactly supported probability measure. I'm going to explain what this probability measure is actually represents. But we say that a sensing matrix lies in a universality class indexed by this measure mu. Okay? If it satisfies three conditions. The first condition is that this matrix can be written as J, a deterministic matrix, times S, a diagonal matrix with IID plus minus one signs. So in this case, the only source of randomness is the additional plus minus one sign modulation on the right. So this is the only randomness we still need to carry. For example, J can be this a spike in sign matrix, which is fully deterministic, but we cannot directly handle this type of matrix. We have to add additional random sign modulation on the right. Okay. The second condition is that the operator norm of J is essentially order one, so they are bounded. As you increase dimension, the operator norm is bounded. The third condition is the critical condition that captures what we mean by the singular vectors being generic. What we say is the following: for any fixed integer k, you look at J transpose times J to the power of k. Okay? So this is again a matrix. And what we're requiring is this matrix is essentially close to a constant times identity matrix. And this constant is exactly calculated from this underlying probability measure. Okay. And by close, we are taking the L infinity norm. So we just look at the maximum difference of all n squared entries of this matrix. We want this difference to be of order essentially 1 over square root of n. Okay, so this is the condition that we would want for any k. So essentially, this is a kth moment of the matrix. We want a kth moment of the matrix to be close to a constant time identity. In other words, we are saying all the diagonal entries of this matrix are essentially constant, all off-diagonal matrix entries of this matrix are essentially close to 0 with a maximum fluctuation size 1/√n. So this is really just the requirement. Now, we can verify for special cases of a matrix that we want to study, this condition is indeed satisfied. A very simple example is the Horng matrix, where we have a diagonal matrix times a Horng matrix. This is our J. And let's just try to verify our condition to see exactly what we get. J transpose J to the power of K, because V is orthogonal matrix, is equal to V times the diagonal matrix to the power of K times V transpose. And V is a Horng matrix. If you have worked with Horng matrix, then you know that every individual column or row of this Horng matrix is essentially like a Gaussian matrix. Okay? And then you can apply very simple concentration inequalities to see that this matrix is very close to a constant times identity, where the constant is just the empirical average of the kth power of the eigenvalues. Right? And you can write this empirical sum formally as an integration of lambda to the power of k with this underlying empirical measure defined as this delta measure on the eigenvalues. Now, here, this is also the point where we need to define a probability measure mu. Probability measure mu is nothing but the limiting distribution of the singular values of the underlying matrix. All right. And for other type of matrix, for example, spike and sign, randomized DCT, and several other type of matrices, you can easily show that the condition is satisfied. Okay, so this is, so it turns out that it is surprisingly easy to show that this condition is satisfied for a very large class of these kind of structured matrices. Right. So now, once you have this condition, then we can prove the following. So suppose we have two different sensing matrices that are coming from the same universality class. Okay. In other words, they have the identical single value spectrum. Now, if you do this regularized least square estimation on these two different matrices, and you get two estimators, beta 1 and beta 2. These are the two different estimators that we would get. And the claim is that if you use any nice test function, then the difference of the test function applied to the beta 1 will have the same limit as applying the same test function on beta 2. So for those of you who have worked on this type of estimation, this is a totally natural setup. But for people who have done this, you might not really directly get what I mean by a test function. But you can think about a special case of test function. The test function is a minus b squared. For this particular case, this formulation implies that the mean squared error of the first estimated beta 1 is the same as the mean squared error of beta 2. Okay, so suppose you only care about mean squared error, but this test function allows you to get additional information. For example, you can claim the densities are even the same. So okay, all right, great. So I want to just give you a very high level explanation of the underlying proof idea. It's a very high level. We want to look at this regularized least square by solving this optimization problem. At an abstract level, you can think about the estimator as a function of the matrix X. Because you give me a matrix, you can go ahead and go to solve this optimization problem, and you have your estimator. So this is just a function, but very complicated function of the matrix X, right? And we want to show this function is insensitive to the choice of matrix X if I use different matrices from the same universality class. Of course, this is very challenging because the function is not explicitly defined. It is implicitly defined through an optimization problem, right? So it's difficult to work with this function. So one idea that the first idea that we can take is to take an algorithmic approach. Because this is a convex optimization problem, we can approximate this solution by an iterative algorithm. For example, you run proximal gradient descent. And you know that if this problem is strongly convex, then you can run this algorithm for a small number of iterations, you get very close to the optimal solution. And then what we want to show is universality for the algorithm itself, instead of the direct final result. Okay, but why do I like this algorithm? Because this algorithm is very simple. On a very high level, this algorithm boils down to a combination of two operations. One, matrix vector multiplication. Second, entry-wise nonlinear transformation. Okay, so what we want to show is for a combination of these two operators, the final result is insensitive to the choice of matrix X if they come from the same universality class. So this is really the key idea. And then we studied a very general class of first order methods. I don't want to go to the details. And what we show is that this type of method can be reduced to something called vector approximate message passing. And then in our actual proof, what we proved is that vector approximate message passing is universal if you have different choices of the matrices. And the way we prove it is by using a combinatorial analysis with moment methods and so on. So this is where the technical heavy lifting happens. But then once you have done that, you can show that if you have universality for A and P, then any first order method will have universality because there's a general reduction. And in particular, proximal gradient descent has universality. And because of that, regularized linear regression has universality. So this is a general high-level argument of the proof. I'll be very happy to talk to you about the details offline. Right. So I'm going to move on to the second part, maybe a little bit faster, but in case there's any question, I'd be happy to. Yes.
For example, do you need to fix T and let the dimension go to infinity?
So
You need to fix T and let the
yeah,
dimension.
so officially the proof T is finite and let n go to infinity. Although if you work harder, then T can be a small polynomial n to the power of epsilon, where epsilon is sufficiently small. But for our purpose, finite T will be sufficient because we want to prove convergence of probability. Then you set a finite tolerance epsilon, and then you can then T is a function of epsilon that grows very slowly. So. In particular, for given epsilon T is finite, T epsilon is finite, does not change.
It's independent of the.
Sorry?
It's independent.
Because here we are assuming the underlying optimization problem is strongly convex with a finite lower bound on the Hessian. So the number iteration is independent of n. Yes.
So that shows asymptotically they are same.
Yeah.
There will be the rate of convergence be different.
Yeah, it's a very good question. So we do not have the rate. So it's possible to get the rate from the proof, but I don't think our current approach is the right way to do it because we're using moment calculation, and then it's not very convenient to get the rate. Yeah.
And from your numerical experiment, will be the rate of convergence the same? Like if the size of the matrix are the same?
Yeah.
Because they have similar performance. Yeah, they even have.
We have not done very careful numerical simulation, like what you were suggesting, like you change n on a log scale and then see what is rate. Because we suspect that for matrices, even from the same universality class with different construction, they might have different rates. So that's the reason why we didn't do that careful check. Yeah.
Here the linear convergences of proximate method is pretty important here.
Yes.
That's why
So
you want to consider this elastic net instead of the.
yeah, but you can think about this as a different point. So essentially, the essence of what we've shown is generic first order method like gradient descent, proximal gradient descent, so on and so forth. They are universal for any finite number of iterations. So if you are dealing with a non-convex problem, then you might not be able to say much about the final converged result, but you can at least say if you run your gradient descent for finding a large number of iterations, these two systems are equivalent.
But if you consider directly consider Lasso, can you show the same result? I mean
So yes, that's why we were saying that if you directly consider Lasso, then it's a function of the matrix, but it's a very complicated function of matrix. That's why we want to say we approximate it by something that is complete. Iteration of matrix multiplication with shrinkage and then matrix multiplication and shrinkage. Yeah. This is the strategies that we take. Yeah. All right. So I've 10 more minutes or
think we can go on to the third.
Okay, so I'm still going to be quick. So,
Yeah.
So the second part is about a universality phenomena in context of machine learning, kernel methods, and random feature models. So, so the first part, the mantra or the intuition is that in many problems you can forget about the singular vectors. Singular values are all what matters, as long as they're singular vectors are generic. The second part. The key message is that in machine learning, in many cases, you are studying nonlinear models because of the importance of nonlinearity in a neural network. But in certain cases, we can show that a nonlinear model is equivalent to a linear model plus noise. Okay, so that also allows you to dramatically simplify the task of analyzing this type of models. So this part is a joint work with my former student Osama Difala, Honghu, and with my colleague Horng-Tzer Yau. Now, so just as a reminder of the setting, so we have a classical random matrices where suppose you start with a data matrix X with independent entries. For example, the columns of X are independent, rows of X are independent, for example. And then typically you want to study X times X transpose. You can think about this as an empirical covariance matrix or the grand matrix, right? And then we know that the spectrum of this covariance matrix is described by the Marchenko-Parser law, depending on the aspect ratio between D and N, right? Dimension and number of samples. You can also think about a non-symmetric case where you have a product of a F matrix, which is independent of X matrix. So it's also possible to precisely characterize the singular values of this type of product. But what I'm going to present next are nonlinear versions of these random matrices. For example, you start with this grand matrix, and then you apply a nonlinear entry-wise nonlinear operator on each matrix entry. Okay? Or you can apply this nonlinear function on F times X. This type of operations appear in problems such that if you want to shrink, you're shrinking the covariance matrix, or it also appears in kernel methods. If you want to study a kernel random matrix and sigma will be your kernel function, it also appears in random feature models. So I'm going to start with the example of a random feature model. I'm going to explain what I mean by random feature model. Now, this is just a reminder of the simple setting of supervised learning. What you have are training sets, and you want to do binary classification. Now, in the original input space, maybe the classification boundary is nonlinear, and a typical strategy is you first do a feature map, mapping your original data to a feature space, with hope that in the feature space, the data points are linearly separable. Okay, and then you can do a linear classification. Now, if you want to do linear classification, you can just solve an empirical risk minimization problem where W, this is the vector that you search, is a parameter specifying your linear hyperplane, separating hyperplane, and you solve an optimization problem where L is the loss function, R is regularizer. And the loss function can be, for example, logistic loss, L2 loss, and so on. So forth. Yeah. Now, very popular strategy for getting the feature map is to run through a neural network where the input is your original data and output of the neural network is your feature vector, right? So this is the current strategy. Of course, the weights of the neural network are also learned in the process. But what I want to consider is a simplified model, so-called random feature model. In the random feature model, you're going to assume that the feature map is implemented through a neural network, but the weights of this neural network, here in this case represented by a matrix F, is random, and they kept fixed. So initialize this network with random weights, but you don't train these weights. They don't change during the process. What you train only is the last layer weights. So after the random feature map, and then you learn the last layer weights that does this linear classification. This is a very simple model, but it's pretty convenient for getting theoretical analysis and also can provide some insights of actual neural networks. Okay? Now, the type of question, the quantity that you want to compute are the training error or the testing error. The training error is the value you would get by solving this minimization problem. The testing error is if you are, suppose you get a new sample, and then what is the performance of the classification, right? Based on your trained network, right? Now, what is the challenge? This model is still not straightforward to work with because the challenge comes from the sigma, the nonlinear transformation. Here, in the example of neural network, you can think about sigma as a ReLU function or tanh function. Okay. Now, even if you allow yourself to assume that your weight matrix is Gaussian, your input data is Gaussian, but because you apply this nonlinear transformation, it's no longer Gaussian, right? So it destroys the possibility of using any tools that are developed, that have been developed for the Gaussian or invariant models. Okay? But fortunately, we can still use universality, so we can consider the following two constructions of feature map. The feature map on the left is the one that we want to study, right? You apply X is the input data, F is a random weights from the neural network, and sigma is ReLU. Okay? Now, an alternative construction of the feature map is the following. So you have a linear combination of three components. The first one is constant mu0 times O1, just O1, it's a constant. And the second part is mu1 times F times X. So F times X, this is as if sigma is a linear function. Okay? Mu01 plus mu1 F times X, as if sigma is a linear function. But you add one last part, mu2 times Z, where Z is an independent Gaussian matrix. So this is, the B version is a linear but noisy feature map. Okay? And the mu0, mu1, mu2 are three scalar coefficients that you have to calculate using some formulas. I'm going to come back to these formulas later, but let's just say there's a way of choosing these mu0, mu1, and mu2. Okay? Now, for the two versions of feature map, you can compute the training error for A and training error for B, and training error for testing error for A and testing error for B. Now, there's been a conjecture made in the literature starting from 2019 that for generic feature matrix F, feature weight matrix F, and for reasonable sigma, if you numerical simulations on the A model versus B model, the training error and the testing error are asymptotically equivalent. So if you try a sufficient large P, in this case, the dimension 2000, you get identical performance. Okay, this is the conjecture. And let me just show you some simulation results. Here we have two figures showing the testing and training errors of two supervised learning models. And the orange dots are the nonlinear feature model, and the black crosses are the linear Gaussian model. You can see clearly they fall right on top of each other. It's pretty easy to convince ourselves that there is indeed universality or equivalence going on. And here we have changed different nonlinear functions, ReLU, or in this case, tanh, different loss function, quadratic loss versus logistic loss. They have the same type of phenomena. And this is also a very useful phenomena. Why? Because the B version, it's a linear version with additive Gaussian noise. So it's a Gaussian model. So we have a lot of tools for analyzing this type of model. So with my former student, Osama Difala, we analyzed the training and testing error of the B model. So the detail doesn't matter. So the gist of the result is that when the dimensions are large, the training and testing errors converge to deterministic constants that can be precisely characterized from your model. And here, the green line and the blue lines are the theoretical curves that we can derive based on the linear Gaussian model. Right? So this is very useful. If you know that the original nonlinear model can be characterized by the linear Gaussian model, then you have a lot of tools for precisely analyzing this kind of model. The question is why? this is the case. So I'm going to give you a very simple intuitive explanation for this equivalence phenomena. So if you have the A version, the B version, there are two, you can think about these as two random vectors. If you choose the mu0, mu1, mu2 correctly using this formula, then you can show that the A version, the B version, they have the same first order moment, meaning the expectation vector are essentially the same. The second order moments are also match with each other. So the covariance matrix A version is essentially the same as the covariance of the matrix P version. Okay, so this is, then you can say this is again just a very simple example of universality because I'm matching the first two moments of these two random vectors, and then if you have enough of them, then a lot of the macroscopic behaviors should be the same. Okay, so in our work we made this intuition precise by proving the equivalence under some technical assumptions. We need to assume there's a convex loss function with strongly convex regularizer. The weight matrix have independent Gaussian entries, and activation function has bounded derivatives and is not function. So this is some technical assumptions that we have to make. Although empirically you don't need to have any of these conditions, you still have equivalence. And then under these conditions, we proved the following result. So let me just go through these results a little slowly because there are a lot of notation. So here, what we are saying is the following. We are saying the training error of the A version, the probability of that to deviate from any constant C by an amount 2 epsilon is upper bounded by the probability of B version to deviate from the same constant by an amount epsilon, plus an additional correction factor. But this correction factor, as P goes to infinity, goes to 0. So essentially what we are saying is the right-hand side, the B version provides an upper bound for the A version. Okay? And the situation is completely symmetric. So you can replace A with B and you get a second line. In other words, as a consequence, if you can show the B version converges in probability to a constant, then if and only if the A version converges in probability to the same constant. But the point here is the B version, the linear Gaussian model is much simpler. We can prove the convergence of constant. And similar result also works for the test errors. So I'm going to skip some of the proof details, but it's just a standard Lindbergh approach. I'd be very happy to go over the details with you offline. So I want to mention that that this type of equivalence can also be extended to Chrono method. So in many cases, you have your training, you have input data xi, and then you want to look at the Chrono matrix, right? It's an inner product Chrono matrix where sigma is your Chrono function. And then there is also an equivalence phenomena that you can exploit. What we do is we first can write sigma, which is a function, as a linear combination of polynomials. And these polynomials are fairly special type of polynomials. So these polynomials are so-called Horng polynomials. Okay? And here I give the first 4 such Horng polynomials. The point of these Horng polynomials is they are orthogonal polynomials with respect to the Gaussian distribution. Okay? Now, a very general equivalence phenomena is the following. So suppose you have decomposed your nonlinear function as a linear combination of Horng polynomials, then the underlying matrix A can also be written as a linear combination of these matrices where each h of I is applying the corresponding Horng polynomial to entries of xi and xj. Okay. Now, what we can show is a fairly general equivalence phenomena. And we go a little bit beyond the classical asymptotic regime where the two variables are linearly proportional to each other. We consider the case where the number of samples is proportional to the dimension to the power of L, where L is any integer. L equal to 1 corresponds to the classical linear scaling regime, but we can consider quadratic, cubic scaling regime, and so on. So we can show that the A version of the Chrono matrix in a high dimensional limit is equivalent to a much simpler version where H of L is equivalent to a Rishabh matrix, and all the other higher order H components are essentially independent GOE matrices. They are just independent matrices with symmetric entries, and the corresponding eigenvalues have a semicircle law. Now, as an application of this result, we get to analyze the precise performance of kernel-rich regression for a very large range of parameter choices. The number of samples versus dimension can be very flexible. For example, number of sample can be linearly scaling with the dimension, or quadratic scaling, or cubically scaling, and so on. And there is precise curve in terms of testing error. And there is also at different phases, there are different non-monotonic behaviors at different phases of this sampling region. Okay. So I don't want to go to the actual details, but again, I'll be very happy to talk to you about it offline. So let me summarize. So in this talk, I presented this very interesting universality phenomenon, which says that many large and complex systems are asymptotically equivalent, although they can be different in their detailed constructions. I don't want to emphasize that universality is a blessing of dimensionality. If you don't observe universality if you work with a 10 by 10 system. You only do it, you only observe it when you're dealing with large systems. But this is exactly the case for many data sets that we're dealing with these days. Now, in the first part, I showed you our work in understanding universality for high-dimensional estimation problems, and the important intuition that we proved is that in many cases you can only care about the singular values, and the singular vectors are not essential. You can replace them by power matrices, okay, as long as they satisfy the conditions that we proposed. And for the second part, we study similar universality problems in kernel random matrices and random feature models. And for the second part, the key message is that in many cases, if you're dealing with nonlinear models, they can be asymptotically equivalent to a linear model with additional noise. Okay, and again, the point here is the right-hand side is much simpler than the left-hand side because of linearity. Yeah, it's just additive noisy model. All right, great. Thank you for your attention. I'll be very happy to answer questions.
Thanks, Professor Liu, for the great talk. Any questions for the speaker?
I have a question. So way back at the beginning, I think it was before slide 20, you had something that kind of looked like a commutative diagram. Yeah, that. So I don't know if this is a good question or not, but like this looks like a commutative diagram to me. So I'm wondering if, and you're talking about like classes and these look like morphisms. So is this like something you could apply something like category theory to, or is that too like way out there?
This cartoon is much simpler than what you're thinking about. What we're just saying is a universality class is an equivalent class. If you can establish a universality class, and then you can identify all the matrices within the same class, then the optimization problems, the performance optimization problems are essentially identical. And then you can pick any particular instance of these random matrices to study, because they are asymptotically equivalent. But the point here is that among matrices in the same universality class, there are ones that are difficult to analyze, but there are also ones that are really easy to analyze. The Haar, for example, is very close to highly Gaussian because it's rotational invariant. So we have a lot of tools for analyzing it. Yeah.
Yeah, suppose you identify an some class of like uniform, what's it called, universality, and then you have a But if you have a data set, how do you know whether your matrix satisfies this one?
Yeah, so it's a very good question. So if you have, so we have some condition, for example, J transpose J to the power of K is close to the constant, but this is still asymptotic condition. Suppose you have a data set or a matrix that is 5,000 by 6,000, but finite. How would you say, you know, is it satisfying condition? Because we have an asymptotic condition. So in some sense, this is still not fully resolved. What we need is something like what Lei was referring to about the convergence rate. So how fast this universality would kick in, right? How large n needs to be for you to be safely apply this universality phenomenon. This is something that we do not have, and we're working on it. But we're trying different proof techniques.
You just have one data set with a fixed n.
So in this case, what you would need is essentially a precise error bound. You have a data set, then you can verify. For example, I can still do J transpose J to the power of K, but I try K up to 20, and then I have I check the difference between J transpose J to the power of K minus that identity times constant, and I have error term, and then I want to translate that error term to error term in terms of MSC. We don't have that yet. We only know that as n go to infinity, the error term go to 0. But we don't know exactly what is the function that maps the error in the assumption to the error in the final result. And this is indeed very, very important to make it fully practical, but we don't have it yet.
So I think due to limited comments, thanks for speaker again. If you have more questions.
Very ambitious.